All right. So the agenda today, just a quick reminder, the Uniform Circular Motion Gizmo is due tonight. And I did have a few students email me over the weekend with a question. It was everyone that emailed with a question about that gizmo had the same question, and it was on part B. So if you have it with you, you may want to pull it out. If you haven't got that far, you can maybe make a note to yourself. If you already finished it, then you probably don't have this question. You figured it out. But on part B, number 3, it says gather data. It tells you what radius to use in the settings, and then you determine from the simulation what the acceleration is. And then there's a row that says radius factor and acceleration factor. So a lot of students have written to say, how do I find that? The same thing repeats itself on the next page for question 7. It tells you the velocities to set, then you take the acceleration from the simulation, and it asks you to come up with the velocity factor and the acceleration factor. And it's a little awkward the way they organized it, but after the table where you're supposed to fill those in, then they give you the directions on how to do it. So for instance, on the table at number 3, the directions for finding the radius factor and acceleration factor are explained in step 4. So in step 4, it says to calculate the radius factor, divide each radius, so the one that they gave you here, 2, 4, 6, 8, 10, by the original, which was 2. To calculate the acceleration factor, divide each acceleration value, which is what you're measuring from the simulation. So you should get 50, 25, so on and so forth. And then divide it by the original, which was 50. And so what they're trying to get you to do is just to see, is the acceleration changing at the same rate as the radius, or are they changing at different rates? That's what they're trying to help you identify. And then in number 7, it gives you those same kinds of explanations. How do you find those factors? It explains it in step 8. So it's a little awkward. I think it would have been better to just have that part in the directions for number 3 and number 7, but it actually comes after. So if you haven't done that yet, make sure when you get to that table, just read the next step and it will clarify what you're dividing to figure out those factors. And then again, the whole goal is in the end, after you do both of those trials, this is very much like what we would do in actual lab in person, is try to figure out, well, what is the relationship between acceleration and radius? What is the relationship between acceleration and velocity? And then we would come up with a mathematical equation from that. Now, you already know the mathematical equation because we talked about it last week, but you hopefully will find from this data the same relationship. So that's what that's trying to get you to do. So if you have some confusion on that, hopefully that clarifies it for you. So that is due tonight before midnight Pacific time. And then today we're going to continue with some notes on uniform circular motion. But like I mentioned last week, they're not really notes in the sense of giving you new vocab words or new equations. Basically, it's just looking at a new kind of problem, a vertical problem. When an object is moving in a vertical circle, what happens? And then in stages, we're going to finish up worksheet 1. So we're going to do a little bit of it now, and then we're going to go to the notes and then learn about vertical. Then we'll come back to the worksheet again. So we'll kind of be bouncing back and forth to that worksheet number 1. So hopefully you have it. Those of you guys in the classroom, there are copies of all the worksheets we're going to be looking at this week on the table over there. So you guys can grab those copies and have them for yourself if you didn't get them last week. I had some of them available last week, but some new ones are there now for this week. And then at the end of the period, we'll either start worksheet 2 together, or depending on how much time is left in first period, I just said, okay, I want you to do the first 2 questions for next time. So it won't be a formal assignment where you got to do all of that worksheet, but I do want you to potentially do a little bit of it. Depends on how much we can get done in class. All right, so that is the agenda. So let's go ahead and switch to worksheet 1 first off. And I'm going to give you a few minutes just to work on your own and see if you can answer question 3 and 4. So we talked about questions 1 and 2 already last week, but I'd like you to try 3 and 4. I'll give you 5 or 6 minutes and just give you time to see if you haven't finished answering those questions to do that now. So worksheet 1, question 3 and question 4. If you've already finished them, you can go ahead and work on question 5, or you can start looking at worksheet 2. But make sure in the next 5 or 6 minutes you have questions 3 and question 4 on worksheet 1 complete. All right, I think most everybody's done or getting there on 3 and 4 at least. So it looks like most of you, it just still came up in participants, so that's fine. I can see it either way. Um, let's talk about number 3. So it says we've got a car entering a circular turn at a constant speed. Name the force or interaction between objects that allows the car to travel in a circle. In what direction does this force push the car? Draw a free body diagram of the car as it approaches head on. So now what force do you think is the force making the car go in a circle?
I put friction.
Good. And then Sally, what direction would that friction force be applied?
I just said that it would be going in the
In.
forward direction of the friction.
Yeah, good. The friction force would be inward into the center of the circle. Excellent. All right, so then if we think about the free body diagram, if we're looking at the car head on, we don't really know which way the car is going around this curve necessarily. It just depends on how you envisioned it. But there are a couple things that we should see. Let me start sharing the screen here with the worksheet. We should see that you have a weight force downward and a normal force upward. And then the friction force has to be perpendicular to the weight, because the weight always is straight down. And we're assuming this is just a level road. So the friction force has to be perpendicular to the weight. And obviously, if it's going around a circle, the actual direction of that arrow would be changing because it'd all be pointing to the center of the circle, but it would always be perpendicular to the weight. So if we're just looking at it head on, it would look something like the free body diagram here. And the net force would be to the center of the circle because vertically speaking, the car isn't accelerating. The car is only accelerating in the horizontal plane. And it's not accelerating in terms of its speed. Its speed is constant, but it's accelerating in the sense that it's changing direction. So since velocity is a vector, as its direction changes, it's accelerating to the center of that circle that it's driving around, that curve that it's going around. And then for part B, describe the motion of the car if the force you described in part A suddenly vanished. And so that would be like you're driving down the road, you're going around a curve, and then you hit an icy patch or a snowy patch or a hydroplane situation where you've got a puddle of water and you lose traction. When you lose traction, I don't know how many of you drive or if any of you have ever experienced that, it's kind of a helpless feeling because no matter how hard you turn the wheel, there's no friction. And because there's no friction, you just go straight. And then usually what happens is your car is intermittently catching and losing friction as you're going across this slippery surface. And so you're turning and not turning, turning and not turning. And that's why you end up losing control and often spinning and having a big problem. But the initial scenario is you go straight. And I've actually had to start thinking about that more these last couple of days. Being in Indiana, they have quite a bit of snow and ice here right now. So I had to be pretty careful turning around the corner to pull into my parents' road here because it was pretty icy. Because I didn't want the car to go straight, I'd end up in the neighbor's yard. So I wanted to make that curve, and I needed enough friction to help me do it. All right, looks like we got a question here. Oh, that's bad. You have experienced it, huh? This week even.
It wasn't even that bad though. Like I corrected it.
Good, good. I'm glad that it turned out okay and that you didn't get hurt or anything. So yeah, it can be a scary feeling when you lose traction. That friction is important. All right, for part for part C, I've had a few myself through the years, having grown up in the frozen tundra here in the Midwest. So part C, what's that?
It was just bad because I was on Decker.
Oh, curvy. All right, part C, if the 35-meter radius turn is level, so again, we're assuming the road's level, and the car has a mass of 1,200 kilograms, and the coefficient of friction between the tires and the road is 0.85, so that's a pretty good high coefficient. What's the maximum speed that a car can travel through the turn? So if we consider these data points, I'm just going to kind of reveal step by step, and you can kind of compare your notes. So the first thing we could think about is, all right, well, to solve any force problem, we want to think about the net force. And if we look at our free body diagram, the net force is the friction force. Okay, so we know how to calculate friction force. We learned that last semester. We take the coefficient of friction times the normal force. We can also see in the free body diagram, the normal force is equal to the weight force because it's a flat road. They're balanced, therefore the car doesn't rise or fall vertically. So we can substitute mg in for the normal force. So we know the net force is mu, the coefficient of friction, times the mass times g. But we also know in this problem, the net force is causing the car to go in a circle. And if that's causing the car to go in a circle, we can call that a centripetal force and therefore a centripetal acceleration. And so that net force, that friction force, is also, in this case, the centripetal force for this scenario. And centripetal force is a generic force. It's not a certain kind of force per se. In this case, friction is what causes the centripetal motion. But because centripetal force is generic, it has a generic equation. Generically speaking, whether it's friction or gravity or tension, or no matter what's causing that centripetal motion, generically speaking, we know it's mv squared over r. So in this case, the centripetal force is friction. In every case, centripetal force is mv squared over r. So we can set those two things equal to each other because the friction force is the centripetal force in this problem. And then using algebra, we can solve for v. We can plug in the 0.85 for the coefficient of friction. They used 10 here instead of 9.8, you can see, and they used newtons per kilogram. You're going to see more and more this curriculum uses newtons per kilogram more and more often. I will tend to generally still use meters per second when I write it, but in this curriculum, they're starting to show you that alternate set of units for the acceleration due to gravity. And then the radius of the curve was 35 meters. So did the mass of the car even matter? No, in this scenario, the mass of the car didn't even matter. And so we can see that the m cancels out when we set those two things equal to each other. And so the velocity is just based on the coefficient of friction, the acceleration due to gravity, and the radius of that curve. Now, if the road had an angle to it, like a banked road, or if it was a different kind of problem, then the mass might matter. But one thing you'll notice is in a lot of these circular moving scenarios, the mass does cancel out the vast majority of problems. So, all right, in this case, we can see that the velocity you could turn around this corner without losing traction, the friction would be sufficient as long as it's 17 meters per second. And the last comment I want to make about this is a lot of times students get a bit confused why we call this static static friction, not kinetic friction. Since the car is moving, a lot of times students say, shouldn't that be kinetic friction? But for kinetic friction, the surfaces are literally sliding on each other. So that would be like when your car's on the ice and your wheels aren't gripping the road, they're actually sliding across the surface. That would be kinetic. But here the wheels are rolling. The rolling part of the wheels is what's making the car move. But the fact that there's grip, the fact that the tire doesn't slip on the road is what allows you to turn. And since we don't want the tire to slip, that's static friction. There's enough grip basically to allow the car to push back to the center of the circle. If the tires were sliding across the surface, that would be kinetic friction. So sometimes for vehicles that have all vehicle problems where there's tires involved, I guess not so much a plane, but for these kind of problems, that friction is a static friction because it's what's creating the grip. Any questions on number 3? All right, number 4, International Space Station orbits Earth once every 90 minutes. Name the force that allows the ISS to orbit the Earth. So Aiden, what did you come up with for the force that allows the space station to orbit?
Earth's gravity, because it pulls it into the center.
Very good. Earth's gravity. And then Evan, part B says, explain why the space station doesn't crash to Earth due to this gravitational force.
I said because it has enough velocity to hold it in its trajectory in orbit.
Good. And hopefully now we're also recognizing that velocity is tangent to the circle, right? So the velocity is one direction and the acceleration due to gravity, this gravitational force field, is perpendicular to that. So we have this perpendicular force to this velocity vector. And so that creates that orbital motion where we've got an acceleration one way, no acceleration the other way, but there is movement. And so the combination of that non-accelerating movement as velocity and that accelerating movement on this plane creates an orbital type of path. All right. So that is 3 and 4. We've made it through those. We'll come back to number 5 after we do some notes. So let me switch back to the not PowerPoint, but the Smart Notebook. We're going to take some notes. I guess, like I said, I don't know if notes is quite the right word, because it's really just thinking through some other kinds of problems you're going to see that have the same sort of logic, baseline logic that we've learned, but different scenarios. And so we're going to talk a little bit about vertical uniform circular motion. So almost all the problems we've talked about so far, we could think about them as horizontally oriented, like this car going around a horizontal road, or the bowling ball being curved by hitting it with a mallet, but it was horizontally on the ground. Now we're going to talk about, well, what if it's vertical, like a Ferris wheel or a roller coaster or something like that. So we're going to look at a variety of different kinds of problems College Board likes to use, a couple of different scenarios they like to use for questions. One is anytime you have a curved path. And so this object, no matter what it is traveling along a curved path in part of its motion. And if we want to analyze it right where the dot is, let's say that the object is right where that dot on the curve is. So not the dot at the center of the circle, but the dot on the curve. If that's where the object is, then we want to draw a circle. We call it the kissing circle, because the circle is going to sort of match with the curvature, but specifically touch right where the object is, sort of kisses the circle or the curve right where the object is, so that the radius of the circle and that velocity are tangent. So you're making the circle kiss just right at that spot on the curve, so that the velocity of the object and the acceleration to the center of that kissing circle are perpendicular. All right. Drawing that kissing circle is going to help us determine what is the direction of the acceleration. So that object at that instant right there on that curve would have an acceleration to the center of the circle, because anything moving in a circle is changing direction. It's curving around the center of that circle. And so at that instant, this object has an acceleration directly to that center of the circle. All right. So drawing the kissing circle helps us figure out which direction the acceleration is. Now, this particular problem, this would be a pretty tricky problem, because that acceleration is at an angle. It's not on the X and Y axes, nice and neat, like the main ones we're going to look at today. We'll look at some more angled things in days to come, but for today, this would be a pretty hard one. We're not quite ready. I want to get a little more comfortable with some straight X and Y scenarios first. So let's use that idea, but with a slightly simpler scenario. Let's put the curve at the bottom instead of on the side. So we're thinking about a car driving on a hilly road. And could I get someone to read this slide for us? Someone in the Zoom to read this one?
I can do it.
Thanks, Ethan.
All right. When a car goes through a dip, we can consider it to be in circular motion. Its acceleration towards the center of the circle, curvature, which is up in this case. Its acceleration is towards the center of the circle. Okay. We can use a free body diagram and Newton's second law to derive an equation for the normal force of the car. Since the acceleration is upward, the normal force must be greater than the weight force, and the net force is centripetal because it causes the car to move towards the center of the circle.
All right, thank you. I'm going to give you just about a minute or so to process that a little bit, look at the picture, look at the math, maybe jot a few things down, and then we'll discuss the picture and the math. All right, so in the picture first, we've drawn a kissing circle here that matches the curvature. And we've got the car right at that point on this kissing circle where its velocity would be tangent to the circle. But the advantage of drawing the kissing circle is we get to see, we know that it's centripetal motion here. We know it's circular based motion. And now that we know where the circle fits, the acceleration is always to the center of the circle, because that's literally what centripetal means if we translate it, right? It's center seeking. So if we know where the circle is, then we know the acceleration is to the center of that circle. That means the acceleration for this car at that position on the kissing circle would have to be up to the center of the circle. If the acceleration is up, the upper force, the upward directed force, in this case normal force, would have to be greater than the downward force, in this case the weight. Otherwise, if they were balanced, there would be no net force and there would be no acceleration. If the weight was larger, the acceleration would go in that direction. So we know because the acceleration is upward, the upward force has to be greater than the downward force. So in this case, the normal force has to be greater than the weight. If we think about the math then, we know, as always, Newton's second law applies, and we just modify Newton's second law to help us solve problems. So one way to think about this is Newton's second law is the sum of all the forces, and there's only two. There's the normal force, which is up, and the weight force, which is down. We know the normal force is greater, so we would subtract normal force minus the weight force. We also know, though, that net force is just, more generically speaking, ma. And in this case, because it's centripetal in nature, we can substitute v squared over r for the acceleration. So we know the net force as a sum, normal minus weight, and we know the net force as ma. In this case, we're modifying that to be mv squared over r. And because we have a lot of that information, we could solve that problem. What do you notice about the well, let's hold off on that question. I'll bring that up on another problem. One thing I want to mention though here before we go on, if you have trouble figuring out, well, what do I subtract and what do I subtract from what, like if that part is complicated, if you're struggling with that a bit, you can just use the whole vector idea. So let me kind of show you. I won't do this much, but I want to do it at least once. So if I think about adding these forces as vectors, if I just say the normal force plus the weight force equals mv squared over r, and I just think about them as vectors, if I take that vector kind of mentality, the nice thing is you always add, it's vector addition. But then you have to make sure you define what way is up and what way is down. Since the acceleration is up in this problem, I think probably upward would be the best way to say positive is up and negative is down. So the normal force is up, therefore it would be positive. Weight is down, therefore it would be negative. And then this acceleration, because remember this v squared over r is the acceleration, right? The acceleration is up, so it would be positive as well. So if you're going to use the vector method, you just have to figure out what's positive and what's negative based on how you define it, and then put signs on those values to reflect that. Now, in this problem, it's going to end up looking exactly the same. The normal force is positive, the mv squared over r is positive, and the weight's negative, so we end up getting the same look. But it's just a different mental approach to solving the problem. So if you get to one where you're struggling with, oh, I don't know what to subtract from what, just make them all positive, make them all not positive, but make it all addition, and then decide what's positive, what's negative, depending on your direction vectors or the direction of your vectors. All right, questions about that one? All right, what if the car is going over a hill? Can I get one of you guys in the classroom to read this one for us?
Sure. When a car goes over a hill, we can also consider it to be in circular motion. Its acceleration is towards the center of the circle, which is down. We can use a free body diagram and Newton's second law to derive an equation for the normal force on the car. Since the acceleration is down, the weight force must be greater than the normal force.
All right, so if we wanted to take the vector approach, I'll just go through it again one more time for practice. So if we want to take that vector approach, we would just say, well, the net force is the sum of the forces, normal plus weight. And it's going to equal, it is a centripetal force. So we're just going to use this centripetal scenario here, the centripetal equation. And now we need to say, okay, well, what's positive and what's negative? So we could stay the same way as before, that up is positive and down is negative. That's tradition. If we do that, normal force is positive, weight's negative, and centripetal force over here on the right would be negative, because so we would have positive for this, and then negative, and then negative. Okay, so we just have to make sure we use the signs. Or we could switch it and say, no, let's not do that. Since the acceleration is negative, let's make the downward direction positive. Then that would make this negative and that positive and that positive. So as long as we're consistent, we can make positive whatever direction we want. And we can always just add, because it's vector addition. And we just have to make sure our signs reflect what we choose to be positive and what we choose to be negative. Now, I don't normally do it that way personally, not because it's worse or anything like that. The way my brain works, I like to think it through conceptually. But that vector method may be really helpful for some of you. So if that's something that benefits you, do it. There's not a way you should do it. Nat, that's fine. Did you hear me, Nat? Okay, she must have. Okay. For the other way, the way I would tend to do it, I would not use the vector method normally, just personally. It's just my personal preference. I would say, okay, in this case, we know that the acceleration is down, so this one has to be bigger. So I would say mg minus the normal force. Take the bigger one minus the smaller one. And then that's still going to be equal to mv squared over r. And now I don't want to add pluses and minuses for vectors in, because I'm not using a vector approach. I'm just using more of a conceptual approach. So either way works. Just don't mix and match them within a given problem. If you start a problem with the vector approach, stick with it. If you start with a conceptual approach, stick with it for that problem. Don't try to mix and match in within one problem. It's really easy to make a mistake if you do. So questions on that one? All right, so real quick, going back a slide. If you were in this car at the bottom of this hill here, bottom of this valley, at that moment, would you feel heavier or would you feel lighter? Heavier. The normal force is bigger, so you feel heavier. How about here at the top of the hill? You're going up over the hill. Would you feel heavier or lighter?
Lighter.
Lighter. Your weight's not really changing, but you feel lighter because your body's inertia has an upward component to it. So your body wants to keep going upward. And so that normal force is a little bit less on you. If you're going fast enough, you might even leave the seat. You might have enough inertia to keep going, like on a roller coaster. That's why you wear seat belts. Or if you've ever been in a car going really fast over a hill, you may have come off the seat a little bit, right? Because your inertia has enough of a vertical component and you're not as massive as the car is. So the car has enough mass to stick to the road, but you don't necessarily have enough mass to stick to the seat, right? Or on a roller coaster, the roller coaster is attached to the track by the rollers, but you aren't necessarily attached to the seat unless you got seat belts or a lap bar or something like that. So that's the kind of thing you want to think through as well. Do I feel heavier? Do I feel lighter? Kind of going back to the same sort of conversations we had about the elevator problems in January. All right, so now let's actually start working through solving a problem mathematically. A car is traveling at a velocity of 20 meters per second. The driver of the car has a mass of 60 kilograms. The car is located at the bottom of a dip in the road. The radius of this dip is 80 meters. What is the apparent weight of the driver? And the apparent weight is the normal force supplied by the seat of the car. So we know the weight of the driver should feel heavier or lighter here.
Heavier.
Heavier. Down at the bottom of that, they're going to feel heavier, right? Just using 10, what's the weight of this person? Using 10 for G.
600 newtons.
600 newtons. So when we solve for the normal force, it should be more than 600 newtons, right? They should feel heavier than they really are. Just kind of, And I know sometimes we talk about this and you may think, well, why do you ask us all these questions, Mr. Webb? We can just solve the problem and find out. If you understand what it's supposed to be, then you know if you're on the right track when you get an answer. So I would always encourage you to try to think through the problem, make some predictions. All right, so let's go ahead and start solving this. So first, if you aren't given a picture, you probably want to sketch the problem, because then you can draw the kissing circle, figure out which way the acceleration is. Once you know the acceleration direction, then you can start figuring out which force is greater than the other force. So if they don't give you a picture, draw one. And if they do give you a picture, they probably won't draw the kissing circle on it. So I would encourage you draw the kissing circle on it so you make sure you know what way the acceleration is. In this case, the circle's above the road, so the acceleration is what direction?
Up.
Up. All right. So then when we look at the free body diagram, if the acceleration is up, the normal force has to be bigger than the weight. The upward force has to be larger than the downward force to have an upward acceleration, because the acceleration is caused by the net force, whatever's left over when we add them together as vectors. Okay, any questions about coming up with the free body diagram or how to draw the kissing circle? All right, let's keep moving. So the dotted lines here represent our X and Y axes, and you don't necessarily have to draw these on here. This is just a quick step, and you can see the bottom part here. It says all forces are parallel or perpendicular to the axes. So there is no need to resolve any vector into components. So this isn't necessarily anything that we need to do for this problem. They're just trying to highlight to you that if you did draw your X and Y axes on here, you would see that everything falls on those axes and just kind of confirms, don't worry about X and Y components, no trig necessary for this problem. All right, a reminder here that they're asking us for the apparent weight, which we know is equal to the normal force. That's what we call apparent, or the normal force is sometimes referred to as apparent weight. And we want to apply Newton's second law. Well, since it's in a curve, it is circular in nature. So we know MA can be changed to MV squared over R, because of the circular nature of this movement. But we also know the normal force is bigger than the weight, so we could say normal force minus weight. So if we combine that logic together, like we did before, we're starting with Newton's second law. One way to say it is add up the forces. In this case, the normal's positive, the weight is negative, or the normal's bigger and the weight is smaller, so we would subtract the weight from the normal. On the other side, mass times acceleration. In this case, it's moving in a circle, so that acceleration would have to be v squared over r. Now, we want to find apparent weight. That's what the question asks. So we want to isolate the normal force. So we would add mg to both sides. And now this next step, I would say, is not really necessary for this problem. So this step right here, isolating the m, factoring the m out, it's not really necessary. So I wouldn't probably do it, but they have. And I believe the reason they have is there are some problems in the future we're going to do where that can be beneficial. So I think they're doing a little foreshadowing here, trying to plant a seed that sometimes that can be helpful. In this problem, I don't really know that factoring out the mass gives you any benefit at all. So I probably wouldn't, but it's okay if you do. And as you see, if we plug the numbers in, the person had a 60 kilogram mass. Acceleration due to gravity, because we're on Earth here, is 9.8. The velocity was given 20 meters per second. We do need to remember to square it because the velocity is squared in this equation. And the radius of that circle of curvature was 80 meters. And we find out the normal force is 888 newtons. Now, that's not to the correct sig figs, and I don't want to focus on sig figs today. We can other days. Last time we focused quite a bit on it. Today, I want to really focus in on the concepts. So just so you know, that is the wrong number of sig figs, but let's just focus on the rest of it for today. But what we can see is this is much more than the 600 Newton weight that we said the person had, right? And we said that the normal force should be bigger. They should feel heavier at the bottom of this curve. And mathematically, we can see, yes, they do. They would feel 888 Newtons instead of 590, or 600 if you use 10. All right, questions? Are you okay with the steps there? All right. So let's move on and expand our thinking through other types of things that could ask. So on a flat road, the driver's weight, which would be the normal force, is going to be equal to mg, because if it's on a flat road, the car's not accelerating up, the car's not accelerating down. Therefore, the normal force and the weight force would be balanced. They would be congruent. And if they're congruent, then the weight is the normal force in magnitude. And so if we use 9.8, you can see here it's 590. So in summary, we know the apparent weight on the flat road's 590. We know at the bottom of this dip, it's 888. They feel much heavier at the bottom of that dip. The gravitational force on the driver doesn't change, but her apparent weight does. So she feels heavier at the bottom of that dip. Is there a situation where she would feel weightless? Maybe we can rephrase that. When would she feel weightless?
When she reaches
Oh,
the top.
You'd have to have a hill.
And how would you have to be traveling on that hill?
Right at the top of the hill.
And probably all of you have felt some bit of this before, whether it's in a car or on a roller coaster. Right at the peak of that hill, you kind of feel yourself lifting off the seat a little bit, right? And if you got to the point where your velocity was just the right value, where you didn't fly off the seat, but you basically lifted off the seat to just the right value where you're technically touching it, but it's not pushing against you anymore. Like it's balanced. You've just relieved that normal force, basically. That would be where you haven't sort of flown off the seat, but you're just about to, right? So that would be when you feel weightless. All right, now this is something that NASA does along with, I think in conjunction with the Air Force, if I remember correctly. But they try to capitalize in their training for astronauts on this whole idea of apparent weight. Because if you're in the space shuttle, if you're in the space station, you have this apparent weightlessness. You're in free fall, going in an orbit around the Earth constantly. And if you've never had a chance to feel that feeling for long periods of time, you can have a lot of trouble with sickness because you're in constant free fall. It's like on a never-ending roller coaster hill. So to help astronauts start to adjust to this, one thing that they do is put them on what they call the vomit comet, which is a plane where they go up to a really high altitude and then basically nosedive. So the plane is basically in free fall. And so everyone inside the plane is also in free fall. And so since the plane's in free fall and the people are in free fall, they're all falling at the same acceleration. And so they're floating inside this plane. So their perspective is that they're weightless. They're really just falling, but they feel weightless. So they feel like they're going to feel on the space shuttle or the space station. Now, they also often invite college groups to join. And so I have heard of some colleges where they have different physics and engineering groups that get to, and sometimes even biology and chemistry groups, they get to ride on the vomit comet and perform experiments to see how the experiments change in free fall, to see how the experiments change in sort of a unique apparent weightlessness scenario. And so they use it for training NASA astronauts, and other also research gets done on this vomit comet. But they call it the vomit comet because they usually, it's not like a roller coaster where it lasts for a minute or so. It's, it's going to last for half hour, 40 minutes while they're going up and coming down and going up and coming down and going up and coming down. And so after a few of those, sometimes people do get a little bit ill. And so that's where the nickname came from. All right, two other scenarios that you often will see College Board use for question types is buckets and roller coasters. Could I get someone in the Zoom to read this slide for us?
Sure.
Thanks, Aiden.
Outside of cars driving on hills, we can see applications of circular motion in other simple ways. Have you ever been on an upside down roller coaster and not fallen out? Turns out the same properties of circular motion are responsible for your safety on a roller coaster.
And depending on the ride, it may have had something to do with seat belts and shoulder straps and stuff like that as well. But normally they're designed so that technically, even without those, you shouldn't fall out. But yeah, it depends on the ride. So let's talk about buckets first of all. So that's the roller coaster connection. So buckets, and you can try this at home. Just grab a bucket, can be any size, doesn't matter. Here they're talking about a bucket tied to a string or a rope, but you can just hold it in your hand. You don't have to tie a string or a rope to it. And just fill the bucket with water or sand, maybe halfway or 2/3, and then start swinging it in a circle. And as you swing it in a circle, you're going to feel the tension in your arm change. So at the bottom of the circle, you're going to feel the tension in your arm being really taut. It's going to pull on your arm because your arm is trying to pull the bucket back into the circular path. But then when you get to the top of the circle, it's going to feel really light because now your arm is pulling it down, but the weight is also down. So they're going in the same direction. So just try this sometime. It could even be like just a bucket of paint. It doesn't even have to be something it could be a closed bucket of paint if your parents are nervous about it, but just like swing that heavy object, or it could be a kettlebell, like anything, swing it in a circle, and you'll notice at the bottom, you feel the tension of your arm pulling it back into the circle. And at the top, if you're going slow enough, it'll stay in that circular path, but it'll feel almost weightless at that top if you get right at that right velocity. If you're going real fast, you'll still feel some tension at the top, but it won't feel as much as it does at the bottom. And if you go too slow, it won't fulfill the circle. It'll start to go up and then it'll break the circle and come down at a weird angle. Right. So you can experiment with that with basically anything of significant mass. In this case here at the bottom of the swing, the bucket has weight that's downward and tension that's upward. And the bucket is being forced to turn back into the circle. So the only way it would turn back into the circle, back to the center, would be if there's an upward acceleration. So at that point at the bottom, the tension has to be larger than the weight. So going back to like what we did in the car scenario, we use our Newton's second law. The tension minus the weight would be the net force or the sum of those vectors. And because it's circular in nature, we can change the generic MA to a different generic MV squared over R. Generic for centripetal. All right, now at the top though, the bucket's different. Like we said, at the top, it's going to feel lighter. So the bucket on the string moving in a vertical circle is also in circular motion. When it's at the top, there's no upward force. The tension is downward and the weight is also downward. So therefore, the acceleration is downward. And the net force then would be the tension plus the weight. And since they're going in the same direction, we would just add them. We wouldn't subtract them at all. And then the net force is also mv squared over r, because if it's going fast enough, it's still traveling in a circle. So there is that point where it would be weightless, where that tension would basically be zero, and it would just be the weight that's making it stay in the circular path. Now, sometimes in questions, in fact, pretty frequently in questions, they will ask you for things moving in vertical circles to determine the minimum velocity that object can maintain the circular path. So like I said, if you're swinging a kettlebell or a bucket of paint or a bucket of water, if you don't go fast enough, it's going to break off of that circular path and come in a different angle. And so the question is, where can we make it minimum so that it stays on the circle, but I don't have to pull on it anymore when we get to that peak? Like I get to that peak and it's just my arm can be totally relaxed and it's going to stay in its circular path. And that would be when the tension is zero. Right? If they're saying what's the minimum, that means I don't have to pull on it anymore. The weight is sufficient, because we can't make the weight disappear. Objects have weight because of gravity and their mass. So we can't make the weight disappear, but they're saying, what about when the tension is zero? So now instead of tension plus weight, if the tension is zero, it's just weight. But the MA is still mv squared over r. So if we solve for v in this scenario, v ends up being the square root of gr. And so we can see here in this problem, the mass does cancel out. And we can see that we could find the velocity as long as we know the radius of the circle and the value for g. Now, I don't know that I would necessarily memorize that equation, but if you are keeping that list of a variety of equations that you may want to keep in your mind, or at least be reminded of when you're preparing for tests and exams, this is one I highlighted because it can be helpful. It does match a very particular kind of question, so it may be a little too specific to worry about memorizing it, but if you want to add that to your list, that would be an option of one you may want to consider. All right, so now let's switch gears to roller coasters. The roller coaster is just like the bucket of water in terms of the forces, but instead of tension, it's normal force again. So it's like kind of a crossbreed of the tension from the bucket in terms of how they match up, but with the normal force like the car on the road. So it's a little bit of kind of both things merging together here. And so it's the same as the bucket in the sense that at the bottom, the normal force is up and the weight is down. So you would subtract them. But at the top, the normal force and the weight are both down. So you would add them, right? So it's like the bucket in that sense. But it's like the car in the sense that it's no longer tension, it's normal force. Because the road stays underneath the roller coaster, the rack or the trail, the rail stays underneath the roller coaster at all times. Other than that, you think through it in the same way we did the bucket. All right, let's wrap it up with a few questions here. A roller coaster is on a track that forms a circular loop in a vertical plane. If the car is to just maintain contact with the track at the top of the loop, what's the minimum value for its centripetal acceleration at that point? So when you think you know the answer, go ahead and type it into the chat. This one seems to be giving a little pause for thought here, trying to think this through. The minimum value would be when you don't need a normal force, the weight is sufficient. So there's your hint. All right, starting to get a few people coming in with answers, and all of you that have given an answer so far are agreeing that it is A. It would be the value of G in the downward direction. What we're basically saying is, like we did with the bucket, that it's just the weight. It doesn't matter what the tension is, because the tension would be 0 at that point. But with the roller coaster, we're just saying the normal force is 0. It's that minimum value. So there's basically saying the normal force is 0. So all that's left is mg. And if we look back at this problem, when we have mg equals v squared over r, the m's cancel. So they're saying g is the centripetal acceleration at that point. And it's the same way for a roller coaster. The g would be the centripetal acceleration when there's no normal force required. That would be the minimum speed. It doesn't need any normal force to push back. All right, 11. A roller coaster again, mass m is on a track that forms a circular loop, radius r, in a vertical plane. If the car is to just maintain contact with the track for the top of the loop, at the top of the loop, what is the minimum value for its speed at this point? Got some agreement, several people picking B. Even though this was a bucket scenario in this slide, it's the same idea. When it's minimum velocity, that means there's no tension in the bucket. That means there's no normal force for the roller coasters. It's just mg. So if we solve for v, it's going to be square root of gr. So that would be selection B, the square root of g times r. That would be the minimum velocity at which the normal force is 0 and the roller coaster is just going to go through based on its own weight. All right, 2 more. A pilot executes a vertical dive, then follows a semicircular arc until it goes straight up. Just as the plane is at its lowest point, the force of the seat on him is less than mg and pointing up, less than mg and pointing down, more than mg and pointing up, more than mg and pointing down. So this is the vomit comet scenario. Pulling out of the nosedive and angling back up. All right, seeing a few more of you answer and a little more rapidly this time. So I think you could even imagine at the bottom when it's starting to pull out of that nosedive, you would feel heavier, just like at the bottom of a dip in the road, you feel heavier. So that is going to be C. You feel your weight feels more than your actual weight, but the direction of its velocity or of its acceleration will be upward. All right, last question. A ball is whirled on a string as shown in the diagram. The string breaks at the point shown. Draw the path the ball takes and explain why this happens. Now, remember, we're talking about vertical circles. So this is not swinging a ball over your head like we were doing in the lab simulation or in the demonstrations before. This is swinging the ball in a vertical circle, all right, like a around the world yo-yo kind of trick. So what would happen to the ball? It's traveling clockwise here in a vertical circle, and the string breaks right here. What would the path of that ball look like? So you can type it in the chat, or if you just want to unmute and say what you think, that's fine too.
It'd be a parabola that like starts going tangential to the circle, but then reaches a point at the top and turns around and comes back. And it
Okay, why would it have that parabolic path? Why wouldn't it just keep going at that tangent?
Because there's gravity, and when we study, so it becomes a projectile as soon as the string breaks and makes projectiles follow the parabolic paths.
Good, yeah. So it's becoming a projectile. And so that path would start at going tangent to the circle, but gravity is going to turn it into projectile. We're going to see this parabolic nature. It's becoming a projectile because it was a vertical circle. And this is one kind of question that often trips up students. They'll think, oh, it's just going to go tangent to the circle because we spend so much time focusing on that. And if it were a horizontal surface and everything was on a flat surface, that would be true. It would just go tangent to the circle. But because this is a vertical circle, if you've ever been on a swing and you swing back and forth and you're in circular motion, right? You're not going in a full circle, but you're in circular motion. And then you jump off the swing. You start tangent, but you don't stay tangent because gravity pulls you back down. So you become a projectile and you follow a parabolic path and land back on the ground. So next time you're on the playground, swing on the swing, jump off the swing, and feel that feeling and think about the physics. All right. So what I would like you to do next is get that worksheet number 1 back out. And I want to put you in breakout groups for about 5 minutes. We're not going to spend very much time, but I want you to see if you can figure out number 5, the last question on worksheet 1. It's based on what we just did in our notes. So if what we did in our notes today made sense, then you shouldn't need more than 5 minutes to answer those 3 parts, 5A, 5B, and 5C. But I am going to put you in breakout rooms so that if you need a little bit of help, you could have some conversation and discuss it a little bit. So let's get some breakouts going. Like I said, no more than 5 minutes. So be pretty short. Looks like you're going to have 2 in most groups, 3 in one group. So have a quick conversation, see if you can answer question number 5, and then we'll come back and wrap that up. All right, I think everybody's back in the same area now, at least virtually speaking. So let's go ahead and talk through 5A, B, and C. Johnny, tell me what you came up with for 5A.
For 5A, I just drew, it's kind of maybe a little hard to explain, but a little normal force diagram that we've done in the past. So I have two perpendicular lines that are flat as described in the problem. And then I have the arrow going up for normal force and the arrow going down for the force of gravity. And I'm not sure if I was supposed to put this because they didn't really specify, but to the right, I put the force of thrust. I don't know if they said if the roller coaster cart was accelerating or with thrust or not. But I put that, and then if that was the case, then to the left would be a little force of friction. So.
All right, good. So a couple of quick comments on that, just so you're all aware of how to think through College Board's process. So unless they say that you should consider air resistance or friction or drag, you assume it's negligible. And again, unless they say there's some sort of thrusting force that's causing an acceleration, you would assume that that's not the case as well. So like on an accelerate or on an actual roller coaster, for the vast majority at least, they use some thrust to push the roller coaster up to the top of a hill. And then once it goes down that first hill, there is no more thrust force. It's just its motion. And so they're generally thinking about those points in the roller coaster's ride where there's no motor causing the roller coaster to move at all. And again, unless they say you should think about friction or air resistance, normally we just ignore it. So the fact that you put those on there is fine, but all they're really wanting you to focus in on are the two that you initially described, that normal force that would be vertically upward and that weight force that would be vertically downward. And they would have to be balanced, because if they weren't, the roller coaster would rise or fall. And it says it's on the level track. It's not rising or falling at this point. All right, Kyle, how about part B? What did you come up with for 5B?
I put an upward normal force, and then equal to that a downward gravitational force, and it's as well as smaller acceleration force. And I said it's not balanced, and there's a net force due to acceleration, and the net force is negative or going downward.
Okay, good. So there is a downward net force, and therefore there is a downward acceleration. And one way you can kind of see that would be that the kissing circle would only be able to work underneath this curve if we were going to draw that kissing circle. It sounds like you had three forces, though, if I understood what you said correctly. And the centripetal force isn't a separate force. And so we never want to think about it as something you would add to a free body diagram. So, and the weight force is unchanging. So if I were to compare these two, however big I drew this weight force on the first one for 5A, I would ideally want to make it about the same for 5B, because the weight of the roller coaster won't change. But the amount of push that the track has to provide changes. So on level ground, it has to only support the weight of the roller coaster. It doesn't have to help redirect the inertia at all. It just is purely balancing the weight. In this scenario where it's at the top of the hill, that roller coaster is going to have some inertia, making it want to travel tangent to that curve. It's going to want to go straight, which means it's going to feel a little bit lighter, which means technically the track doesn't have to be as strong at that point. The track doesn't actually have to bear as much of the weight. And so there isn't actually a third force. It's just that at that point, the normal force would be less. And so while the weight force doesn't change, the normal force does. And so like you had it correct in terms of that there would be a downward net force and a downward acceleration, but there's not a third force that causes it. It's just that the normal force would be less at that point. Does that make sense? Any questions about 5B? All right, Evan, how about 5C?
5C, I said, well, I drew the diagram with a larger normal force and a smaller gravity force. And I said they were unbalanced. The net force is due to the centripetal acceleration to change the direction.
Good. Yeah, nicely phrased in your explanation and clear that it's unbalanced. Again, if you drew the kissing circle, you could see that this time it would have to be above the track, which means the acceleration will be upward. The weight force can't change. It looks like they may have drawn the weight force a little shorter here. Ideally, you would want to have that weight force be the same for A, B, and C, because that's not changing, but the normal force would. So if you were the engineer designing this roller coaster track, on the flat level parts, it has to be strong enough to bear the weight of the track, of the roller coaster. On the top of the hills, it doesn't have to bear the full weight because there's going to be some inertia. And so the normal force can be actually will be a little bit less. But at the bottom of the curves, it has to be more structurally sound, because at the bottom of the curves, the normal force has to bear the weight of it plus redirect its inertia to cause it to curve back towards the other direction to match that circular curve. So the normal force would increase at that point. So if you think about, if you go to next time you go to Six Flags or some sort of theme park like that with roller coasters, look at the supports on different parts of the track. Is there really much support at the top of a loop? No, because there's not as much normal force needed there, but there's going to be a lot of support coming out of that loop on the bottom side and at the bottom of curves. You're going to see a lot of footers and support beams underneath the bottom curves. And so just keep that in mind next time you go to Six Flags. Get a little geeky, think about the physics, and then so you can still have some fun. All right, so that is all for today in terms of new material and thinking, well, not really new material, but new kinds of problems and finishing up worksheet 1. Now, what I'd like you to do before we meet next time, and well, not next time, actually, next time Wednesday will be, since it's a Wednesday, we're just going to do AP review. So I'm going to give you actually a long FRQ to practice on Wednesday, and we'll do some peer grading this time. So instead of you grading your own, we'll have you trade with somebody else and have them grade it if possible, assuming there's at least 2 people in the classroom, and we'll put you in breakout rooms for those of you that are virtual, and we'll see if we can try to trade documents in some way so you can read each other's or read it to each other's and see if you can give each other feedback, use the rubrics to grade each other's papers, and see how you do on a long FRQ with forces. So that'll be Wednesday. Thursday, though, we're going to continue going through more and more problems like this. So before Thursday's class, I would like you to get worksheet 2. So for those of you guys in the classroom, worksheet 2 is over there on the table. I think you picked it up earlier today, or you may have even picked it up last week. I did have them out towards the end of last week. So make sure you have worksheet 2. If you're virtual, make sure you print it or open up a digital copy of it. It's in unit 7. So unit 7, worksheet 2. And I'd like you to try questions 1 and 2. So you don't have to do the whole worksheet, but I just want you to try questions 1 and 2, and they are about roller coasters. They're going to be like what we just did here with question 5, but they're going to actually give you numbers. So you're going to have to do some calculations with it instead of just thinking of it conceptually. Questions? All right. You are dismissed. And if you have questions, stick around to ask them, but otherwise, I'll see you next time.